Hello, I'm Longxi from FastLab Zhejiang University. Now let me introduce you the paper, an efficient trajectory planner for car-like robots on uneven terrain. Nowadays, many tasks require ground robots to navigate autonomously on uneven terrain, such as rescue, fire transportation, and exploration. But none of existing 2D indoor navigation techniques can be directly adapted to uneven terrain, since most of them ignore the fact that some properties of the terrain, such as height and curvature, will change with spatial location. Planning on uneven terrain requires two additional considerations. The first one is the traversability of the terrain. In this scenario, both trajectories are executable for the robot, but the pink one is better because the area around the green trajectory is much more rugged and the risk is greater. The other is robot's dynamics model coupled with terrain. For example, if the robot needs to go up here, it may need more amount of throttle to overcome gravity. If it is not considered in planning, the controller may not track the planned trajectory well. Attributed to the nonlinearity of the terrain, the high-dimensional robot space, most existing works cannot address the second problem well. So in this work, we consider that the interaction between the terrain and the robot can be described by a mapping of SE2 to R times S2 positive, where S2 positive denotes the upper hemispherical surface. Using this mapping, we designed an efficient optimization-based planning framework for car-like robots, which allows to considering both the first and the second problem effectively. On flat terrain, the state of the robots can be represented by a point in SE2. On even terrain actually change the height and altitude of the robots. R in this mapping represents the space bounded by the height of the robot, while S2 positive represents the space bounded by the z-axis of the robot's body frame. With this mapping and the ZXY Euler angle representation, we can obtain the SE3 states of the robots on uneven terrain. We proposed an algorithm to construct this mapping approximately, but because of time constraints, we won't go into detail here. The details of the algorithm and the results of a construction of the mapping can be found in the paper and the open source code. Based on this mapping, we model the planning of a car-like robot on uneven terrain as an optimization problem and solve it. To show the efficiency of the planning framework, we built different simulation environments in gazebo and compared with some existing works. Our method has multiple advantages. In this scenario with mountainous terrain, we compared the velocity curve of the trajectories. It can also be seen that our algorithm better utilizes the manual variability of the robot. We also did real-world experiments in this case. In this case, we require the robots to traverse two terrain models made of foam with distinct raised area, obstacles, and slopes to test whether the proposed mapping can help the planner generate safe and dynamical feasible trajectory. This table shows the variation of relevant variables during the motion of the robot. The robot maintains a relatively high speed and small checking error during the process. This video shows small tests we did. Although our method has a lot of advantages, there's still a huge space for improvement. We didn't consider the suspension system of the robot, which is very important for robots to navigate on extremely rugged terrain. Also, in these more complex scenarios, it's very challenging to get accurate dynamic models of the robot in contact with terrain. In these cases, we may resort to a combination of other tools such as neural networks. In the future, we will consider these factors and extend the proposed framework to more difficult environments. Okay, that's all. Thank you.